Okay, now we're going to talk about the efficient frontier of risky assets. We're going to look at a graph that represents portfolios that maximize expected return at each level of portfolio risk. So three methods. We have maximize risk premium for any level of standard deviation, maximize a standard deviation for any level risk premium, and maximize a Sharpe ratio for any standard deviation or risk premium. So what they're talking about here, and this is the expected return as well as the standard deviation. So we're looking to try and hit some of those lines on the left-hand side for a lower standard deviation, but start our way, really we're looking for that line E more than anything else, to construct a portfolio that falls along those lines, where my expected return can be higher, my standard deviation is lower. So we're looking at like E and F in this case. So for the points A, B, and C here, they represent expected returns and standard deviations of three different stocks. The curves passing through A and B show the risk combinations of portfolios formed from these two stocks. So similarly, the curve passing through B and C shows the risk analysis formed by those two stocks, by B and C. Now observe point E. It's on the curve, or the AB curve, and point F on the BC curve. These points represent two portfolios chosen from set A, B, and BC combinations. The curve that passes through E and F in turn represents a portfolio constructed from portfolios E and F, since E and F themselves are constructed from A, B, and C. So A, B, and C are kind of the main portfolios here, but E and F, those points are ones that we take elements of A, B, and BC, and we put them into one single portfolio, and that's our diversification we're doing, to create a portfolio that gives me that line there at the EF line in this particular graph or this particular chart. The efficient frontier risk analysis, the maximum variance in the portfolio. So we have our expected return over here and the portfolio standard deviation down here, just like we had in the prior chart. The analytical technique that we use to derive this risk asset was developed by a guy named Harry Markowitz. It's also called the Markowitz model, which you can look up too. And so first thing we have to do is we have to determine the risk amount involved. So choosing an optimal risk portfolio, we want to make sure that our capitalized asset line tangent, our portfolio capital asset line tangent to the efficient frontier. So the closer we can get there to that efficient frontier, this top part here, the closer we can get to that, the better off we are. Now, what you're usually going to see, this is the maximum amount that we can do. So really, generally speaking, this is a mathematical maximum. So generally speaking, we're looking to get in that range, so we're getting somewhere in that ballpark. With what we're doing, we don't really expect to ever actually get right perfectly there. Unfortunately, it'd be nice if we could. That's a really tough spot to hit. Separation property implies portfolio choice separated into two tasks. First, we determine the optimal risky portfolio, and then our personal choice of best mix of risky portfolio and risk-free assets. So an illustration of our optimal risk portfolio: if it's efficiently diversified global portfolio using stock market indices of 6 countries, standard deviation and correlation is estimated from our historical data, and then our risk premium forecast is generated from a fundamental analysis. So this would be the efficient frontier, this blue line here. This German, China, US, UK, France, those would be my individual countries. And what we're talking about, since we're building this from indexes from countries, those would be the 6 countries that we see, 1, 2, 3, 4, 5, 6. Those would be the indices that we are investing in from each country. And then you can see the minimum and maximum variance with no short sales versus having short sales. And then we have right here in the middle, there's when it's optimal to have a short sale. And then you see your CAL, or capital allocation line, goes along right here. So an index model relates stock returns to returns on a broad market index and firm-specific factors. So remember, indexes are things where we take a group of stocks and add them together, put them all in one place. And when you see things like the Dow Jones does this, or the S&P 500 does that, they're talking about index. Excess returns is anything that we get above the risk-free rate, so our return that we get outside of that. A beta is a sensitivity of a security's return to a market factor. So a market factor could be a lot of different things. Let's say it's the housing market. So a beta factor would be a factor that we use to estimate how much a stock or a security of some kind is going to move based on a factor, in this case, it's the housing market. So a beta factor could be, let's say a beta factor is 2. And if that were the case, for every 1% that the market went up, or that the housing market goes up, if my beta factor is 2, then that stock should go up by 2%. By the same token, if it goes down by 2, it should go down, multiply that by 2 and go down by 4. So beta, again, can be positive or negative. If it's negative, then it goes the opposite direction of in this case, the housing market. Whereas if we're positive, then it goes the same direction or follows whatever that market factor is that I'm using. Firm-specific or residual risk is a component of return variance independent of market factor. So this is specific to the individual firm or organization. And then alpha is the stock's expected return beyond that induced by the market index. So my excess return, RI equals beta I RM. This is a component that's due to movements in the overall market. So beta I is securities responsiveness to the market. And remember, the beta is just how much it changes based on what the rest of the market's doing. The alpha here is the stock's expected excess return if the market factor is neutral, i.e. the market index excess return is 0. And the E is the component attributable to the unexpected events relevant only to this security, which would be this firm-specific aspect. So we have our beta, we have our alpha, and we have our firm-specific issues. The statistical and graphical representation of a single index model. We're talking about how we represent, what indexes, and using indexes as one of our markets concepts that we can figure a beta or an alpha off of. And we can graphically represent this. So, for example, security characteristics lines is a plot of the security's predicted return from excess return on the market. So that would be, if we're looking at a specific security, how much more is this going to gain based on what the market has done, or how much less. So in this case, we're talking about excess returns only. So this is the algebraic representation of the regression line. Sorry, it's going too fast. Statistical and graphical representation of the single index model. The ratio of systematic variances to total variances. So systematic or explained variances divided by our total variances gives us our ratio of one to the other. And then we can take that and plug that into our this is not plugged into. This is my systematic or explained part, where this is my total variance down here. So my beta is a part that is at least partially explained. So this is a scatter diagram for Ford against the market index. So you can look at how Ford is done, and where the market index is itself. Sorry, hold on one second. I forgot to turn my page for some reason.